Hey, AGS1, this is a quick video just to help you with a review of the week. I'm going to go through lessons 1.1, 1.2, and 1.3. You can have your notebook open and just be adding things to your notes, highlighting extra examples, and feel free to pause, fast forward, rewind this video as needed. So you can see here that we started in a lesson called checkerboards. Now, the idea behind the checkerboards was that there was an empty space in the middle. You can see that that yellow um, that yellow outline square in the middle of that checkerboard. And the idea behind this one, excuse me, the idea behind this one was that we were looking for a quick and efficient way to count these colored tiles. Now, we had all kinds of counting methods, right? You came up with a lot of them in class. That was really neat to see. So one that I'm going to highlight today, and this is just one of many, was this one. We said, well, we could group the ones in the middle, and it looks like on this 5 by 5 square, we would have 5 groups of 5. And then what would be left over would be these 4 corners, or those 4 groups of 2, or 8. So we rewrote that and we said, okay, well, that's 4 groups of 5 plus the additional 8 for the ones around the corners. So that was a quick way to find, yes, we do actually have 28 colored tiles around this 5 by 5 square. But bumping that up a little bit, we said, you know, what if we didn't have a 5 by 5 square and we had 10 by 10, 20 by 20? Well, then what? Once we get into some bigger numbers without feeling fairly confined in having to draw it, we said, well, if we made this, let's say an n by n, as opposed to a 5 by 5, we could just take that n, or I'm sorry, we could take the 5 out of that expression, and in its place, we could insert an n. And now all of a sudden, we have a formula. Eventually, we call this an explicit formula, where we can plug in any number for n. We can plug in 10, and we could say 4 times 10, which is 40, plus 8, which is 48. So now we have 48 colored tiles if we in fact have a 10 by 10 square in the middle. So that was a neat way that also ties into some function notation, which we looked at a little bit later as well. So that was the overview of lesson 1.1. Okay. Next, we looked at 1.2, which was an idea called growing dots. We looked at how to visualize that pattern, and the one that came up the most as we were visualizing was this one. At the beginning, we saw that one dot, and we noticed that that one dot carried all the way through to each one of those additional minutes. And then we noticed that there was 4 added to that one dot after 1 minute. At 2 minutes, we had the 4 from the previous minute plus the additional 4 as well. So most of us saw this as a way, when we described it, we use terms like you're adding 4 each minute, something along those lines. So we put that down into a table and we said, okay, that means at minute 0, we have 1 dot. At minute 1, we've added 4 more for a total of 5. At minute 2, we have 9 dots, and we kept going from there. At minute 3, we had 13, and so on and so on. So we looked at the table this way and said, hey, looks like every time, which is what we saw from the picture as well, but we can see it in the table. Here's where it comes up in the table, is that we added 4 each time. So this type of sequence is called an arithmetic sequence, because it has what we call a common difference. Now, the common difference is what we see over here. It's the plus 4, plus 4, plus 4. It's the number that we're adding, or subtracting for that matter, but in this case adding. It's the number we're adding every time. And that's how we'll know it's an arithmetic sequence, because we have plus or minus the same number each time as we go down in the pattern. or as we go across in the visual. So we also looked at these terms called a recursive, whoops, I didn't mean to erase that. I meant to highlight that. We looked at a term called a recursive formula and an explicit formula. So we found in a recursive formula, it was kind of nice because we could just take that formula and say, well, every time if I want to get the next term, I'll take the previous term and add 4. So it's just talking about the pattern every time it clocks up, in this case, a minute. Okay, now the explicit formula came from our pattern. And the explicit formula here we use to find the nth term. So this one is helpful if in fact we wanted to find how many dots at, let's say, 100 minutes. I don't want to draw this pattern 100 times. Nobody has time for that. So if we have an expression where we could plug in a number, see what comes out, then that's really helpful. So we found that it looked like here was, if you can consider that little at the beginning dot, our +1, here's what we noticed. We noticed that those 4 were added, like we said earlier, were added every minute. So for every minute, there was 4 more dots added. At 2 minutes, there were 2 groups of 4. At 3 minutes, there was 3 groups of 4. So at 100 minutes, there would be 100 groups of 4 plus the 1 in the middle. So we had to think about the pattern here. And then we noticed that that would be 401 dots at 100 minutes. So we simplified that down to say, well, that means at n minutes, we would have 4 groups of n, or n groups of 4. We could say it either way, plus the 1 in the middle. And that was a good way of looking at how to, an easy way to determine down the road how many dots there would be at a certain number of minutes. All right, this is our final review one for today. So this was 1.3, and this one was called growing dots. And the difference we noticed in this pattern, if you look at the beginning with these 3 dots, we noticed pretty much right away that when we went ahead to 1 minute, every dot, so if these were the same dots earlier, then the dots just doubled, almost like everyone had a partner. And we can see the same thing over here. So if we started with these, now if we have 2 each time, then those 2 also got a pair over here. So we were fairly confident that as we looked ahead, we could continue that pattern to 3 and 4 minutes. As we looked ahead, if we were describing that, we would say, well, it looks like we're doubling our dots every minute, or times 2. Several of you mentioned that as well. Doubling every minute. So if we go to the table, at 0 minutes, or in the beginning, we have 3 dots. At 1 minute, we have 6 dots. 2 minutes, we have 12. 3 minutes, we have 48, and so on. Okay? So it looks like this one, if I look over here to the side, I'm multiplying by 2, multiplying by 2, multiplying by 2. This is a different type of sequence than the previous one, isn't it? Because in the previous one, we were +4, +4, +4. So this is a different looking sequence. This one is called a geometric sequence. And it has what we call a common ratio. And the common ratio is that number over here, times 2, times 2, times 2, that's being multiplied every time. So if you think about it as a ratio or maybe a factor, it's increasing by 2, okay, multiplied by 2 every single time. So that is what we call a geometric ratio. So when we think of this in terms of a recursive formula, we would say the next term is the previous term times 2. And the explicit formula, we had to spend some time on that explicit formula. This one was a little bit different to think about. But when you think about this in terms of multiplying by 2, here, let's start. I'm going to put a little bubble off to the side here just give us some thoughts to think about here. We started with 3, didn't we? And then we multiplied by 2, okay, every time. Let's say that we just did that and just looking, let's say at the 2-minute marker there. So we multiplied by 2 once, multiplied by 2 again. And when we think about those exponents in a repeated fashion like this is when we want to use exponents. So I'm just going to multiply by 2 one more time over here. Okay. So if I think about it like this, I want you guys to remember that when we use exponents, we can say that's 2 times, now this group right here, these 3 2's, 2 times 2 times 2, I can write as 2 to the 3rd power. So what we eventually came to as we were thinking about the explicit formula here was we needed to use exponents to simplify that repeated multiplication. So we came up with a formula, that said 3 times 2 to the n power. So that meant, let's say, for example, I wanted to find out minute 20. I would take 3 and then multiply by 2 20 times in order to find the answer to that one. And we had to be a little bit, we noticed that that number got really big really fast. So that was something that we had to consider. Okay, so lastly here, lastly is function notation. So the idea behind the function notation and why it was particularly helpful for us in this case is, let's say, for example, we input the value of 4. So the idea of a function is you input a value and then you get out what happens once you kind of crunch that number through the expression. So in this case, with our explicit function, we take 3 times 2 to the n power, and if n is 4 in the case of this function, then we will raise 2 to the 4th power and then multiply it by 3. So let's think a little bit about what 2 to the 4th power means. 2 to the 4th power means we have multiplied by 2 4 times. Okay, 2 times 2 is 4, times 2 is another 8, is 8, and then times 2 is 16. So 2 to the 4th power would give me 16, which is this right here, times 3 would be 48. So that means in a function, if I input 4, I get out 48. In other words, at 4 minutes, I have 48 dots. And it's just another way to think about, which we can see in our table, but it's another way to think about how functions could be helpful in this case. Okay, so that is a week in review for you. Let me know if you have any questions. Make sure that you've got all of your formatives for this week. There should be 3 of them now total. Make sure you have your formatives finished, and I look forward to seeing you next week. Have a good one.